situation for our bivariate association will be gender and the willingness to get married in the next 3 years. Our sample will consist of McMaster University students in their 3rd year. Hey Nancy, how's it going?
Hey Eric, good. How about you?
I'm alright. What are you up to?
Oh, nothing. Just looking at wedding dresses.
Looking at wedding dresses already? How soon are you thinking about getting married?
Soon, like 3 years. It's always good to be prepared.
3 years? What's with girls wanting to get married so soon?
Hey, that's sexist. It's probably just me, not all girls.
I bet you statistics could prove otherwise.
Oh yeah? How?
Well, first we can survey a bunch of 3rd-year students at McMaster University. Following that, we can create a bivariate table and then use a chi-square test to test the significance between the 2 variables. Following that, we can use bivariate association to test the strength of the relationship between gender and the willingness to get married within the next 3 years.
That sounds like so much fun!
Bivariate association with nominal level variables. The first thing we will do is create a bivariate table for gender and willingness to get married in the next 3 years. Gender is the independent variable and will be in the columns. Willingness to get married in the next 3 years is the dependent variable and will be in the rows. The simplest way to determine if there is a bivariate association is by using the maximum difference. In order to do this, you first must calculate the column percentages by dividing the value in each cell by the column total. Now you must find the largest difference in any row between column percents. For this example, since there are only 2 columns and both have the same percentage difference, it is simple. Based on this percentage, we must now look at table 11.5 to determine if this is strong, moderate, or weak. Since it is above 30%, it is considered a strong correlation. There are several other measures of bivariate association that are more complex and require the value for chi-square to be calculated. In order to calculate the chi-square value, we will follow the steps laid out in Helium Proofs. Step 1. Making assumptions and meeting the test requirements. Step 2. Stating the null hypothesis. Step 3. Selecting the sample distribution and establishing the critical region. Once we have established the degrees of freedom and the alpha level, we go to Appendix C to find chi-square critical. Step 4. Compute the test statistic. In order to complete this step, we need to determine the expected frequencies. Then, the easiest way to calculate the value for chi-square is to create a table that determines the chi-square obtained. Step 5. Making a decision and interpreting the results. Once the chi-square obtained has been found, we compared it to the chi-square critical and decided whether the null hypothesis can be rejected. Since the chi-square obtained is greater than the chi-square critical, we are able to reject the null hypothesis and conclude that the variables of gender and willingness to get married in the next 3 years are related. Now that we have obtained the chi-square value, we are able to continue on to use bivariate association. The measures of association include the existence of a relationship between the variables, the strength of the relationship between the variables, and the pattern or direction of the relationship. The first statistic we will use to test the bivariate association is phi. Phi gives us a number that summarizes the strengths of the relationship between the two variables. The equation for phi is the square root of chi-square divided by n. We will now plug in the value for chi-square that we found earlier. Based on table 11.12 from the textbook, a phi value of 0.35 denotes a strong relationship between the variable. The main weakness of phi is that it only works for 2x2 bivariate tables. In order to bypass this issue, we will now show an example of the second statistic of bivariate association, Cramer's V. In order to show the difference, we will now create a table with a third row. Since we have changed the values in the bivariate table, we must once again calculate the chi-square value using the exact same steps as before with an extra row. These changes create a new chi-square critical of 5.991. Now that the value for chi-square has been determined, we can then continue on with the calculation of Cramer's V. The equation is the square root of chi-square divided by n times the minimum value of R1 or C1. You decide whether to use R or C depending on if there are fewer rows or columns. The value once again denotes a strong relationship between gender and the willingness to get married. Although both Phi and Cramer's V are easy to calculate and are commonly used to indicate the importance of an association, there remains one significant weakness. Even though the values can be described as weak, moderate, or strong according to table 11.12, there remains no direct or meaningful interpretation of the value. This brings us to our final statistic of bivariate association, lambda. Lambda is based on the principle of proportion reduction in error. This means that the statistics are derived by comparing the number of errors made in predicting the dependent variable while ignoring the independent variable with the number of errors made while taking the independent variable into account. To find error 1, we have to subtract the sample size by the largest row total. To find error 2, we have to subtract the largest cell frequency from the column total and then add the subtotals together. Once again, we must look at table 11.12 to determine the strength of the relationship. When we take the value of lambda and multiply it by 100, we obtain a percentage that describes our proportional reduction in error. That is to say, that knowledge of gender in this instance helps us improve our ability to predict willingness to marry by 34%. Although lambda gives us a meaningful number based on its pre-logic, there are still some weaknesses one must be aware of when doing the calculations. The first is that lambda is asymmetric, meaning the value of the statistic will vary depending on which variable is taken as dependent. Secondly, when one row totals is much larger than the others, lambda can be misleading. It can show there is absolutely no correlation between variables when there is indeed one present. This must be kept in mind when calculating lambda.